Thanks for coming. I'm excited to be here. And tonight I'm going to talk to you about some of the stories and pictures that we've discovered about Mars using the Curiosity Rover. But before I start, I just want to do a little bit of review about Mars. Mars is the fourth planet from the Sun, and it's like Earth in many ways, and unlike Earth in many ways. The Martian year is a little bit longer, almost twice as long, and the Martian day is about 40 minutes longer. So we've just last week finished 2 Martian years of activity on Mars with the Curiosity Rover. So we've accomplished a great deal in this time, and we're actually in the extended mission phase of exploration. On Mars, the gravity is about 40% that of Earth, so you'd be a lot lighter, and it's about 44% dimmer on Mars than on Earth, because Mars is 1.5 times further from the Sun. As most of you probably know, the Martian atmosphere is much, much less dense than that on Earth. It's less than 1/100th of the atmosphere of the Earth density. And it's made up almost entirely of CO2. So, and there are other trace amounts of water, oxygen, and especially noble gases. So while Mars is an interesting planet, and actually if you took just the surface area of Earth, that's equivalent to the surface area of the entire planet on Mars. And over the past several decades, we've been able to land a few times on this planet. And we've also tried and failed many more times than we succeeded. So it's been quite a challenge for engineers of the world just to get there. Here's another picture of Mars. And many of you may know that Mars has the biggest volcano in the solar system. That volcano is about 25 kilometers high, so it dwarfs anything we have on Earth. And you also might recognize this big, giant Grand Canyon that's almost 3 times as long as New Zealand and about the same width. So imagine that, and up to 7 kilometers in depth. So these are 2 of the probably most striking features of Mars, and there's one more that is less commonly known. And that is this, it's called the Global Dichotomy. And in this picture, on the top you see the poles of Mars, but what I'd like to focus on is this lower picture. You see the blue and the red. And 2 things to notice. Well, blue corresponds to lower elevation than the orange and red. So the northern part of Mars, the northern hemisphere, is actually 1 to 3 kilometers lower in elevation than the southern hemisphere. And the other thing to notice is that the southern hemisphere of Mars is really pocked with many, many craters, whereas the northern part is pretty smooth. So we think that early in the planet's history, we're not sure quite sure when, but there was either several large impactors that hit Mars close together, or one very large impactor that caused the large fraction, up to 1/3 of the planet, to become liquefied or molten. And that's why you see this younger, or rather this cleaner part of the Martian surface. Now so we know, or we assume rather, that the northern hemisphere of Mars is younger than the southern hemisphere. When we're trying to decide where to land on Mars, we solicit input from the entire scientific community. So anybody in the world, actually whether or not you're a professional scientist or not, you have the opportunity to give input as to where we should land. And after several years of deliberation and winnowing down from about 11 candidate sites, we came upon, for the Curiosity, we landed in Gale Crater, which is right about here. So right between this the boundary of this global dichotomy. The thought was we'd land in a crater that had a central mountain, try to land near the base of that mountain, and be able to explore from older rocks to younger rocks by moving through the stratigraphic record with this Curiosity Rover. So we infer a history of Mars from the pocked surface, which was tied to the lunar cratering record, and also from all of the features we see on the surface of Mars using satellites and telescopes that seem to suggest that the surface of Mars has been heavily shaped by impact craters and by water activity. So we divide Mars into 3 geologic eras, and essentially they're listed up here: the Noachian, the Hesperian, and the Amazonian, and they're distinguished by the amount of water involved in each phase of Mars history. But the overall summary is that we think in the early history of Mars, Mars could have been wet and warm. So it could have been like Earth today with we don't know whether there was life there. And then slowly over time, we went from being wet and warm to slowly drying up, losing the Martian atmosphere, and going to the Hesperian, where we have evaporate deposits that are rich in sulfates, and finally to the Amazonian, where we are today, where Mars is a cold and dry place. Now I'm going to move on to the Curiosity Rover. So Curiosity was picked to explore the Gale crater on Mars, and NASA is pretty conservative in its expectations, because we want to have the most likelihood of success, and so we know it's very difficult to identify life. So rather than look for life with this rover was sent to Mars to look for signs that Mars was once or is or could be habitable. That was the goal. So we wanted to take this rover to Mars, assess the biological potential on Mars, look at the geochemistry and geology in great detail in situ, and also detect whether or not we could find any water, what the weather was like, and whether we could get indicators of paleoclimate on Mars. And then finally we have a radiation monitor, and that's really in place to look at radiation levels and how they fluctuate on Mars, because eventually we're going to send people to Mars. And one thing that's pretty exciting to me is that NASA has plans to go to Mars send people to Mars in the 2030s, and that means that the person who's going to go to Mars has already been born. So that's pretty exciting. It won't be me though. Anyway. So here's another picture of the Curiosity rover, and essentially we're sending to Mars a robot field geologist. So my background's in geology and geochemistry, and so this is exciting. And the idea is we send this rover to Mars, and actually this is a 1 to 10 scale of that rover, so I invite you to come up afterwards and touch it. It only weighs about a kilogram or so. And send it and give it a long, I guess it has a plutonium energy source in the back. So it has a long life, we think, and the ability to traverse many miles over rocky, or I should say many kilometers over rocky terrain. It has a lot of imaging capabilities, and it has the most sophisticated geochemistry and organic geochemistry tools that we've ever sent to another planet. So we want to use the Curiosity to look at, we'll be able to look at many, many samples of both rocks and soils and analyze those in great detail, and then finally use these to evaluate the habitability or the potential for that on Mars. Here's another one, just showing this array of instruments and that are essentially make up the science payload of the rover. And all of the scientific team, so there are actually several hundred scientists who get to work on this Curiosity Rover project, and I'm happy to be one of them. And most of us are assigned to a particular instrument. So for me, I'm part of the ChemCam team. And ChemCam is a chemistry and camera instrument suite that's situated both on the rover and the masthead here. On Mars, we don't see the rover firing, but the rover fires from the masthead up here and can fire up to 7 meters away from the rover. So essentially, it's the geochemistry scout. It can even fire while the rover is moving. So, and then it has a collinear telescoping imager that detects the light that's released, or rather emitted from the plasma that's generated when the laser hits the rock surface. And then we can tell, based on the light that we measure, what the elements are. So ChemCam doesn't tell us the mineralogy, but it tells us the basic elements. Is there iron? Is there magnesium? How much nickel is there? It turns out to be very sensitive for hydrogen, which could be a proxy for water. And so it's an instrument that is highly utilized on this mission. It's the first interplanetary laser. Curiosity also has, I mentioned, weather detectors, radiation detectors, and two, I think, really fantastic, instruments. And these are the SAM, the Sample Analysis on Mars, and the ChemIn. And these instruments are actually inside the body of the rover, so they require a material being scooped up, sieved or sorted, and then brought on board for really in situ analysis. SAM is actually a series of instruments, including a gas chromatograph, a tunable laser spectrometer, and a quadrupole mass spectrometer, and can really look for an array of organic compounds. Whereas ChemIn is an X-ray diffractometer and uses the same tools that we use in geology departments and analysis labs on Earth to really determine exactly and explicitly the mineralogy of the material we're analyzing. Curiosity also has this big arm, you can see right here, that's coming out from the rover, And on this is a very sort of complex array of instruments, including an alpha particle X-ray spectrometer, Martian hand lens imager, and then a whole drill scoop that includes this brushing tool, scooping, sieving tool, and a pounding drill. Curiosity also has 17 cameras, so really it can look everywhere, above, below, all around, even the bottom. So we were actually able to film the descent onto the surface of Mars, and that was pretty exciting. Here's just another schematic showing this fancy tool on the arm. So it even has the ability to prepare a surface we're going to look at, and almost like a transformer robot, swap out, which is the instrument of choice, and then go into action mode. Now on Curiosity, everything is very, very slow because we're very cautious. We don't want to hurt the rover, but it even has spare drill bits and the ability to change those out. So I thought I'd put this up just to show you the progression of robots that we sent to Mars. Many of you may have seen The Martian, the movie starring Matt Damon, and you might have noticed with the little Sojourner rolling around in the hab. So that's the one that came with Pathfinder, that was the lander. It was only 10 kilograms. It was pretty small, like something you actually might play with in your garage. And then the next were the two Mars exploration rovers, Spirit and Opportunity, that weighed about 175 kilograms. Now, those landed in about 2004, I think, December of 2004, and the nominal mission was only a few months for each rover, but Opportunity, 12 years later, is still going strong, so that's pretty awesome. And then we have this giant Curiosity, which weighs almost 1,000 kilograms, and even this arm, it's really heavy. It weighs about 90 kilograms. This is the size of a small car. I like to say it's like the size of a Mini Cooper car. Oh, and there's me for scale. So in the past, we sent landers and rovers to Mars successfully using sort of the bouncing ball technique. The rovers were protected inside big balloons that then as the parachute helped slow the descent to Mars, eventually the balloons inflated, and then the rover or the payload bounced and bounced and bounced, and eventually the balloons deflated, and then the thing could open up. Well, Curiosity was so heavy that wasn't going to work. So I don't know. Did any of you see the movie showing that crazy sky crane engineering maneuver? So that was pretty exciting and pretty terrifying at the same time. But that's how they took Curiosity to Mars, and it was going to have a descent, and then rather than bounce through a ball, after they fired retrojets to help with slow the landing, they're going to actually lower the rover from a sky crane several meters, then have it touch down on the surface. And they've done this with military jeeps on Earth, but many people thought it was a fool's errand or a fool's effort to try this on Mars. And so many of the engineers, the nervousness and then the resulting excitement when it was deemed successful was really palpable on landing day. And as part of the science team, I got to be in the same building with the engineers. They kept all the scientists down in the basement. and the engineers wore blue shirts and could come and go, but they were all super hyper and super smelly. and then super excited. So it was one of the most exciting experiences of my life to be experiencing that from underground. But anyway, and we watched, on the science team, we watched the same things anybody in the world would be watching either online or on TV. So we all shared sort of that thrill of landing this rover on Mars. Here's just a map showing where we have the exploration field sites. So most of the landing sites are near the equator. It's much easier to land, it turns out, on the equator. So, and also there are many interesting sites to look at. But you can see here the Viking 1 and Viking 2 from the 70s. The Phoenix, which was just a lander, not a rover. It was the only one that landed in the high altitudes. And there's Pathfinder, the sort of mothership for the Sojourner. And then we have Opportunity, Spirit, and in yellow, again, showing where Curiosity landed in Gale Crater. And here's a close-up of this Gale Crater. It's about a 154 kilometer wide crater. You can see here, and then this central area is the sort of resurgent dome of Mount Sharp that's about 5.5 kilometers high. And we've actually been able to see stratigraphic variety using the orbital imagers that are currently circulating on Mars. And this little thing right here is the landing ellipse. So the size of the ellipse was essentially it's smaller than the distance between the North and South Island. So it might seem like it's a big playing field or a big target field. It's actually, again, compared to the bouncing ball method, it was quite challenging to be able to land in the site. And they wanted to be able to land in the site so the rover would be well positioned to sort of tool up toward the base of Mount Sharp. Here's another image. These are actually color corrected high-rise images. Same Gale crater, but just from a different angle. And we picked this site again because we think it had perhaps an ancient deltaic fan, and it would be, give us a site that would give us the maximum chance of finding organic compounds or finding evidence of water in Mars' past. And we also, one of the current Mars orbiters has an ability to look for, it has the CRISM instrument that is essentially a reflectance spectrometer. And so we think we see signs of clays and sulfites, again, going from older Mars to younger Mars. So here's just an image here, so showing the heat shield during the descent. And then here's the surface of Mars that's being blown up as the lander's coming down, or as the rover's coming down. And then we have touchdown. And here's the very first image we got looking right at Mount Sharp. And it's pretty amazing, pretty amazing image. And then the chief scientist and chief engineer agreed on this phrase, let's see where Curiosity will take us. So first it took us to Rocknest. Now, in the mission anomaly, we're going to approach the base of Mount Sharp and walk uphill. But based on some of the satellite images, there seemed to be kind of an interesting place not too far away, half a kilometer away, that looked to be a place where 3 different types of geologic units met. So since most of the team we're all essentially geologists, we decided, well, we voted to go to that part and to spend just a wee bit of time looking to see if we'd get a lot of information by looking at 3 different rock types. Well, we ended up spending a lot of time there. And here's what we saw on the way. Here's the landing site, which is named after the science fiction writer Ray Bradbury. And here's the hydrazine and pollution. We've polluted on Mars. Anyway, and here are the rover tracks as we're heading over to this sort of area that marks boundaries between different geologic units. First, we headed toward Rocknest. So what's pretty exciting is right away we saw signs of water processes. So here's an example of, from the ground that was cleaned off and then polluted with hydrazine, we saw essentially bedrock that's a conglomerate. So that's pretty exciting. We've never seen a conglomerate on another planet. How do you make conglomerate? Conglomerates on Earth are stream deposits, typically. We also saw lots of rounded pebbles and sand. And again, people have calculated the energy required to make these rounded pebbles and suggested that would have been water that would be maybe up to your hip or waist. That's a hypothesis. And here's the back to the image, again showing where we landed. But it's sort of in agreement with this model that there's been a alluvial fan deposit near the edge of the crater, and that's flown actually continued down toward the base of Mount Sharp. We also found a meteorite right away on Mars, and we could use the SAM instrument and the alpha particle X-ray spectrometer to look at the geochemistry and see that this was not a rock from Mars. So that was pretty exciting. Although that was another distraction. But we're easily distracted. Anyway, and this is ChemCam, and there are lots and lots of data points here. So one great thing about ChemCam laser is it can fire many, many times without using very much power. So every day we have a small power budget we have to figure out how to allocate. And ChemCam, typically when it fires on one target spot, it'll fire 50 shots. Or as my girlfriend says, pew pew, firing the laser on Mars. In reality, it's very quiet. But anyway, and it's also cool because it can essentially get rid of any dust on the surface of the rocks. So the first 5 or 6 shots show a very, very pronounced dust signature, which has a lot of hydrogen, or it's a hydrated dust signature. And on the other side, we have collected over 800,000 data points with ChemCam, and that means massive, massive amounts of data analysis. Now, I trained as a geologist and geochemist, so I've had to learn all about programming and multivariate analysis to try to go from these lasers data to fictive or predictive geominerals we're seeing here. This graph at the top just shows the red clusters and blue clusters, and we're seeing a pronounced signature of one type of rock or one type of chemistry that's the same no matter where we go in the crater. And that seems to be indicative of a global Martian dust signature, and has a lot of iron and magnesium. And then we have more variety in the other type. And then there's sort of a gradation up to this, I don't know if you can see it, but there's yellow, and that's more of a felsic or higher silica content. So we're wending our way over to here from Bradbury Landing again over to this place, Yellowknife Bay. And on the way, we continue to see just amazing features. Here's a large feldspar-rich crystal. We've never seen something that was simply a layered intrusive rock, right? So seeing this rock was exciting for the igneous petrologists on the team because it suggests that there was more differentiation. So essentially, as underground in a molten magma chamber, the lighter crystals could float to the top, and the heavier ones could sink to the bottom. So you have preferential segregation of these crystals. So seeing these feldspar crystals that were up to a few centimeters in length was pretty exciting. Okay, and on the way we also tested out the first scooping and scouring of a little ripple sand dune. First we stepped on it to make sure it was soft and we could scoop it, and then we scooped and scooped and scooped. So here, practice scoopings. So that was pretty fun. And here's what the scoop looks like. And here's a close-up with a hand lens imager on that arm again. You see the different coarse and fine-grained materials in this revealed from the scooping. And then finally, Curiosity took its first selfie. So, Curiosity has taken many, many selfies. Curiosity likes to take selfies. It's a way to assess any damage or any change to the rover, but it's also fun for us to see how the rover is doing. And during this time, the word selfie was recognized by the Oxford English Dictionary as a real word, and we like to think that Curiosity helped promote that vote of confidence. Okay, so here we are in Yellowknife Bay. Again, you can see the rover tracks captured by the satellite. And look at these features. These are more and more features we're seeing in detail of, looks like sedimentary, shallowly dipping sedimentary beds and deposits. Here's looking back toward the rim of the crater, heading into Yellowknife Bay. And here's some other features. We also saw lots of different fractures of the rocks. So here you can see there's a fracture that's been, or rather a filled fracture that's been filled with a sulfite mineral. So we see different generations of fractures, and from that we can conclude that there have been different generations of breaking or fracturing fluid flow, depositing minerals, typically sulfates like gypsum, and then refracturing. So we think there were episodic fluid flow and condensation. Here's a close-up of some of these fractures. This is on Mars, and this is for comparison on Earth. Here's some other features we see. Lots of little spherules, and these have been seen by the Mars exploration rovers too. We think these might be gas bubbles that were percolating through a muddy stone or something like that, and then lithified. Here's the site of the first drilling campaign. And here's showing we used the brush tool, brushing to clean the surface to get rid of that dust, and before we drilled. And here's the view looking toward Mount Sharp as we have deployed that arm for the first time to drill and bring material on board. So we ended up staying at this site for about 7 months. So it was a brief detour that turned into a big campaign, but the exciting thing is we drilled several times and were able to declare the mission a success after this. Here's some close-ups of the drill sites. We do a test drill first before the final drill, which is several centimeters thick, and it's about the size of a quarter is the diameter of the drill hole. And look, you can see sort of sulfate veins in the core, so that's kind of interesting. And these little dots here, that is a raster of several points from the ChemCam laser. So we can look at material profile in situ at depth and also look at the tailings that come out and look at the chemistry. So what we concluded from this long, brief stay at Yellowknife Bay is that it's pretty exciting. We actually found that this site had mineralogy that would have been formed in equilibrium with water that was very neutral. So water we could drink, drinking water. And in the past, we thought Mars would have been acidic or something like that, and some of the other rover findings suggested it was the rocks were more acidic and more hostile. But the coolest thing, in my opinion, that we found here is that the water that would have been present when these rocks were deposited would have been water that you could drink. And so if there was life there, the life would have been, happy to be there. And we also found lots of, with the SAM instrument, small amounts, but trace amounts of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So in other words, the essential organic compounds necessary for life. And finally, that the oxidation state of these minerals would have been very habitable and provided a source of energy for any microbes or any life that would have been present there. So I'm sort of rattling this off, but this is like a very sort of rigorous, exciting discovery that, hey, Mars geology and mineralogy wasn't too different from what we see on Earth today. It's just that we don't find water there. But the water that was there once was very neutral and water that is essentially supports diverse life on Earth as we know it, as we know today. So I just wanted to show you, we see some different color. We've drilled several times since then, and one thing that's a little bit disappointing is we didn't see a lot of organic compounds. So the SAM instrument can detect things to parts per billion level, and even while Sam was working on Mars, the people were working at the NASA Goddard Center in Maryland to continue to refine the sensitivity of the laser, because they have a flight instrument model back in the lab on Earth. And so we found that the thing that was the most abundant was actually a chlorobenzene. So sort of essentially a gasoline or something. And that's depicted here. But we only saw an anomalous amount of that once, and even then it was only less than a parts per million. So it wasn't a lot of organic compounds. We think that because Mars doesn't have any protection from the solar wind or solar radiation, any organic compounds that would have been either delivered to Martian surface through impacts or present there now wouldn't have been protected from UV radiation in particular, and therefore would likely have degraded. So maybe if we're able in the future to drill deeper, we'll be able to find organic materials, or more organic materials rather. Okay, I'm going to skip this for now. And then I'm going to show you as we continue. So this is how far we got, right? This is our landing site, Bradbury landing site, and this is where we are at Yellowknife Bay. And we essentially went less than a kilometer and stayed there for many, many months. Happy, busy, but heck, we came to the site to try to go up the stratigraphy at the mountain. So then we had a big team meeting in person in Pasadena and voted to, oh my gosh, let's just book it. Let's just book, and by book it I mean let's go really, really fast, like on the order of 60 meters a day. So the rover moves like this when it's moving. And then only a few hours a day that it has to stop and check everything, make measurements, whatever. So, but we decided to go fast and try to make it down toward a place that we thought would be the best and safest way to get up toward that stratigraphy. So I'm going to actually sort of speed along too with some pictures, but show you some pictures as we're going toward the Kimberley, which marked the end of the nominal mission. Here's Dingo Gap. Matthew showed this in his introduction, and this is a great site, although we had to back up from the gap because we were afraid we were going to get stuck. So while we have a lot of great support from three of 5 satellites that are currently orbiting Mars, help relay information from the rover back to Earth. So the way we communicate with the rover is we sit in our offices, work on a computer, and the science team as a group, and using virtual communication tools, we make a recommendation for what to do for the plan of the day for the science. And then after we come to some consensus, we send our requests to the rover team, and then they're the ones who actually get to send the commands to move the rover. But it's a long and very sort of tightly defined process. But anyway, and the program is managed at the Jet Propulsion Laboratory in Pasadena. So there is where they send the commands to the orbiters, who then relay that down to Curiosity. And here's the, I don't know if you can see this, but here's the antenna for communicating with the orbiters, this little black and gold thing. So while we communicate that way, we also have a lot of high-rise, or rather orbiter imagery that helps us pick a traverse route. And in this case, we thought this would be nice terrain to wander over, but we found ourselves slipping. And the other thing that's been happening during this mission is we've had a lot of wheel damage. So maybe some of you have heard that the wheels are cracking and breaking a little bit. And so one way we've gotten or slowed the damage is to, again, pick our routes to be what we think might be the least hostile terrain. Another way is to actually drive backwards. So we spend some time driving backwards, and then we bump, and then we go forward. So it's a little scary to think that the wheels might break, but so far we had the most damage in the first year or so, and now that's been minimized. And we can also watch the rover tracks with more satellite data. So here we see, here we see where we stop, turn around, bumped a little bit, and the rover tracks continue down. And here's actually the rover itself. So that's what it looks like from the satellite. Here's some more features as we're driving toward that site. I mentioned the Kimberley. Here's some other drill sites. We had a few attempts where we tried to drill, and it was almost like the flagstone. So it was a flagstone on top of less consolidated material. So we had to cancel the drilling efforts because we were afraid that we were going to break the drill. And you can, this is kind of cool. You can see this as from the drilling. This is like sort of sand, and it's very fine grain, and it's just sort of been moved around like little landslides from that drilling effort that we had to back out of. Here's another drill hole. And then finally, I want to show you this model for the delta that we think that might be a good model for how this area looked in the past. And also, as we're driving, we see lots of neat features that we see on Earth. Like here's some lake deposits. We see super fine, sort of 5 centimeter thick deposits that look like lake deposits I've worked on in Utah, for example. So a lot of interesting features that look. I mean, what I'm continually impressed with is how what the ground over which we're driving, excuse me, looks like terrestrial. Looks like terrain. I mean, do any of you think that you've seen something similar to this in your back, in deserts or something like that? Except we just don't find plants or bunnies. And here's a sort of an optimistic artistic rendition of one possible 150-kilometer swimming pool that many craters on Mars could have been filled with water, if not completely, maybe sort of temporarily or intermittently to help, or rather while these fluvial processes were occurring. All right, now I'm going to continue by showing you a couple more, just sort of more images as we've continued on the mission. So we've been wending our way from Kimberley along this contact base here. We were going to move down here through this region and up to these stratified units where we think we see hematite, clay, and then sulfates. And here's another map showing this. And here's where we are most recently. We've just been working in this black deposit is actually sand dunes. And since we've been monitoring this area over the past several years, we see these dunes are actively moving a few meters per year. We've also been able to walk around and, just like a real geologist would do in the field, walk around again, make several passes as we move the rover, get the data, process the data, and then say, hey, I want to go back. I want to go back and look again. So we've been able to sort of dawdle a few other times, only for a few weeks though, and really sort of address or assess sites just in the way a real geologist would. Here's another cool feature, I think. Look at these mineral veins. They're just spectacular as we're driving by with fill fractures. Here's another, this is the kind of thing we work with where we're looking at, these numbers here represent sols or Martian days. So I'm going to show you a few images that come from Marias Pass, the Simpson Sandstone ridges, as we're again moving south to get toward these black dunes here. There's the sandstone formation, and the contact with the Murray Formation mudstone. Here's another selfie. One way to tell that this is a selfie is that there's no arm in this picture, because Curiosity actually uses that arm to take pictures. So all the selfies you see will be lacking that big boat anchor arm. Wouldn't you see the arm? Well, what happens is that when the stitching process takes, doesn't have overlap because the arm's moving, so it takes that out of the images. The arm, yeah, that's a good point. You still see the arm shadow. Yeah, sort of a mystery picture. It looks doctored, doesn't it? Anyway, here's another shot showing the Stimson area, and we can use ChemCam to look and find gradations in the silica content section that there was actually leaching of the sandstone, leaving behind different amounts of silica, or rather different fractions of silica. And here's again the high-rise image we'd use to help design our route. Here's looking at the dunes. I don't have a scale on this, but these dunes are typically 1 to 3 meters high, and they're really spectacular. It looks like they're a really cool planetary landscape. Now we're coming to sort of a big, tall dune that's a few meters high. And here's that same dune as we approached it. Here's the most recent Curiosity selfie. Again, armless. And here's a close-up of that sand, the black dune sand. And it really looks like sand we see, right? It's actually andesitic in composition, so moderate silica content. And when we spend hours, looking at the sand, arguing over angularity of the grains and the composition of the grains. And if that sounds like fun to interview, come talk to me, because I think it's great. Anyway, and here's again, just going back to, we're in these dark dunes up here, and moving around. We're hoping to get as far as we can up the lower reaches of Mount Sharp. And so I'm going to I'm just about ready to stop. I want to show you here again. Here we are we're about these black dunes, and we started several kilometers away. We've gone, the rover has traversed about 12 or 13 kilometers, and now we're essentially approaching these features. We're about 5 kilometers away from the clay unit currently. Oh, and finally, I just want to say that that this is not how the laser works. And thank you all for coming tonight and for your attention. I'll take questions now.